Hello everyone. In today's lecture, we'll be studying about the atomic spectra of hydrogen and the Bohr's theory. Okay, so we'll be looking at the atomic spectra of hydrogen as well as the Bohr's theory. Now, move on to the uh, topic. Now, in 1930, Niels Bohr, suggested that the uh, electrons orbit around the nucleus. Okay, now there were certain problems related to this model. First problem was that electron might be expected to slow down gradually. Now, if electrons are continuously moving in the orbit, then there should be some energy loss, and then electron should slow down. But this was not observed. Okay, the atom was very stable. The second problem that arose with this thing was that why electrons move in an orbit around the nucleus. Okay, that why electrons move in an orbit around the nucleus? Why don't they just stay at one place inside the nucleus, around the nucleus? And the third problem was that now electrons are revolving around the nucleus. Okay, and electron is negatively charged, whereas the charge on the nucleus is positive because of protons. Okay, we studied these things in the last lecture, that nucleus is composed of neutrons as well as protons, and nucleus is composed of neutrons as well as protons, and electron is negatively charged. Now, nucleus is composed of neutrons and protons are positively charged. So the overall charge and the charge on neutron is neutral, that is, it has no charge. Okay, so the overall charge on nucleus is positive. The overall charge on electron is negative. So this negative charge should be attracted towards this positive charge, and eventually this electron, should spiral. Spiral and collide with the nucleus, but this thing was not seen in nature. Okay, the atom are very stable. The electrons never collide with the nucleus while revolving around the nucleus. Okay, they stay in a particular fixed orbit while revolving around the nucleus. They never collide. So Bohr gave certain explanations related to these problems. Now, the first postulate by Bohr was that electron did not radiate energy. Okay, it did not radiate energy. Now, what did Bohr said? That okay, so you are saying that electrons will slow down when they move, when they revolve around the nucleus, but they will not slow down because they do not radiate energy. If electrons radiated energy, then they would slow down. Okay, what Bohr said, that electrons do not radiate energy if it stayed in one orbit, and therefore the electrons will never slow down. They will move at a particular fixed speed. They will move at a particular fixed velocity. Okay. Second postulate that was given by Bohr. Now it's a very interesting one. Now, Bohr said that when an electron wants to move from one orbit to the next orbit, it can either radiate energy or it can either absorb energy. Okay, you must have understood it. Understood this. What did Bohr said, that when an electron, okay, this is the electron here. When electrons want to move from one orbit to next orbit, then it should either radiate energy or it should either absorb energy. Now, when will the electron radiate energy or when will the electron absorb energy? If an electron wants to move from a lower orbit to a higher orbit, okay, here you can see this. If an electron this is the electron, it wants to go from this orbit to a higher orbit, okay, then it should absorb energy, okay, then it should absorb energy. When an electron wants to move from a higher orbit to a lower orbit, then it should radiate energy. Let us see an example here. Now we have this orbit number 1, n is equal to 1. We have this orbit number 2, n is equal to 2. There is an electron in orbit number 1. Now this electron wants to move from orbit number 1 to orbit number 2. Okay. Now to move from orbit number 1 to orbit number 2, it should absorb some energy. Okay. When electrons want to move from a lower orbit to a higher orbit, it should absorb energy. Here we have an electron in the second orbit. Now this electron wants to move towards the first orbit. Okay, it is already in a higher orbit. It wants to move to a lower orbit. Now, if an electron wants to move from a higher orbit to a lower orbit, it should radiate energy. Okay, this was the thing which was said by Bohr. Okay, what was the third thing? And now moving on to the third thing, we have that why don't the third problem that was with the model was that the electron should eventually The third problem with the model was that, that electron should eventually collide with the nucleus and spiral inside the nucleus, inward towards the nucleus. Now, what it Bohr said that there is certain electrostatic force of attraction between the electron. This is the electron here. This is the nucleus. Nucleus is positively charged. Electron is negatively charged. So there must be some electrostatic force of attraction here. This is the electrostatic force of attraction. Now, electron is, revolving around the nucleus. So there should be centrifugal force acting here. Okay. Now, centrifugal force push the electrons in the outward direction. Electrostatic force is trying to attract the electron towards the nucleus. Now, they are not colliding because the electrostatic force of attraction is equal to the centrifugal force. Okay. So that's why the electron is not spiraling inward in the inward direction and colliding with the nucleus. So that's why the electron will never collide with the nucleus, because the electrostatic force of attraction, the force that is trying to attract the electrons inward in the inward direction towards the nucleus, is equal to the centrifugal force. Centrifugal force acts in the outward direction. Now that centrifugal force is keeping the electrons away from the nucleus. Okay. So these were the postulates given by Bohr to explain the atomic model. Moving on to the next, we are going to study the hydrogen spectra. Now, when we pass some electric discharge from hydrogen gas, we will obtain hydrogen atoms. Now, these hydrogen atoms, will emit some wavelength. Now, these wavelength will emit some light of certain wavelength. Now, the wavelength could lie in the visible region, it could lie in the UV region, or it could lie in the infrared region. Now, why do they emit this light? Okay. Now, or why do they emit these radiations? Okay. The first thing, we have already studied that when an electron want to move from a higher orbit to a lower orbit, it should radiate energy. Now, when an electron is moving from a second orbit, here we have the electron. When an electron is moving from the second orbit to the first orbit, while moving from second orbit to the first orbit, it should radiate some energy, and this radiated energy could be in the visible region, in the UV region, or in the infrared region. This could lie in visible, UV, or infrared region for the hydrogen atom. Now, if an electron is moving from a higher orbit towards the first orbit, okay, then we call it the Lyman series, and Lyman series lies in the UV region. Okay. Now that means the wavelength of light that is emitted is in the UV region. If an electron moves from a higher orbit, okay, orbit number 3, 4, 5, 6, 7, towards the second orbit, if an electron moves from a higher orbit towards the second orbit, then that series is known as the Balmer series. It lies in the visible region. That means when an electron moves from a higher orbit towards the second orbit, it will emit some radiation. It will emit some light, and this light will have the wavelength of visible region. Okay. If an electron wants to move from higher orbit towards the third orbit, we call it the Paschen series. If an electron wants to move from a higher orbit towards the fourth orbit, we call it the Brackett series. If an electron wants to move from a higher orbit towards the fifth orbit, we call it the Pfund series. And that means that when an electron moves from higher orbit towards the third orbit, or higher orbit towards the fourth orbit, higher orbit towards the fifth orbit, then they will emit some light, and this light will lie in the infrared region. Okay. The wavelength of light that is emitted will lie in the infrared region, and this is known as the atomic spectra. Okay. So I hope you must have understood this thing. Now, what did Bohr said? Bohr said that the electrostatic force of attraction will be equal to the centrifugal force. Okay. Electrostatic force of attraction should be equal to the centrifugal force. That's why the electron are staying in a particular orbit and they are not colliding with the nucleus. Now we know that the electrostatic force of attraction, okay, we know that the electrostatic force of attraction is equal to Z times E square, okay, Z times E square upon 4 pi epsilon naught to R square. Okay. So the electrostatic force of attraction between the nucleus and the electron. Now, electrostatic force of attraction is equal to the centrifugal force. So you can write that centrifugal force, that is mv square upon R, is equal to Z times E square upon 4 pi epsilon naught R square. Okay. Now keeping V square here only, we'll try to solve this. V square is equal to Z times E square into R upon 4 pi epsilon naught R square into m. This r and 1 r from here gets cancelled. So v square is equal to z times e square upon 4 pi epsilon naught m times r, m into r. So this is one equation that we have got. And then Planck said that energy occurs in packets, and that we call as quanta. And the magnitude of that is h upon 2 pi. Okay. Now, when an electron is, revolving around the nucleus, they will revolve in a circular path. So they will have a certain angular momentum, and the angular momentum, they'll have a certain angular momentum. And angular momentum is equal to mvr. Okay. The angular momentum of the electron is mvr. Now, this angular momentum should be equal to the whole number because energy is coming in quanta. Okay. So we can say that mvr is equal to nh upon 2 pi. Okay. We knew that the according to Planck, and the magnitude of energy is h upon 2 pi. But what did Bohr said, that the angular momentum must be equal to a whole number n of quanta. So that's why mvr is equal to nh upon 2 pi. Now let us solve this also. V is equal to nh upon 2 pi m r. Okay. And here we'll square it. So v square is equal to n square h square upon 2 square will be 4 pi square m square r square. So we got one more equation for v square. So here is our first equation for v square. Here is our second equation for v square. Now we can compare this. We can solve this. According to the first equation, we got z times e square upon 4 pi epsilon naught into m into r. And according to the second one, we got n square into s square upon 4 pi square m square r square. Okay. Now if we want to solve this, 4 and 4 gets cancelled, pi and pi gets cancelled. From here 1m, here 1m, from here r, and from here 1r gets cancelled. Okay. Now we'll move this r here, and we'll be having n square h square pi m epsilon naught also. Okay. Pi m and then z times e square. Okay. Now for hydrogen, we are studying about hydrogen. The atomic number of hydrogen is 1, so z will be equal to 1. Okay. Atomic number of hydrogen is 1, so z will be equal to 1. Therefore, the equation will be again, we don't have to write z here because z is 1. Okay. Now moving on to the next one. Okay. Now the atom will radiate energy when it jumps from one orbit to the another. When it comes from a higher orbit to a lower orbit, at that time it will radiate energy. Okay. Now the kinetic energy of electron, let us look at the kinetic energy of electron. Kinetic energy will be equal to minus half m times v square. Okay. Or we can say that energy is equal to minus half m v square. And we know about v square already. So this is equal to minus 1 by 2 times m. V square will be equal to z times e square, where we have already found out about the v square. Z times e square 4 pi epsilon naught z times e square upon 4 pi epsilon naught m into r. Okay. So here m and m will get cancelled out. So we will be remaining with 1 upon 2 times z e square upon 4 pi epsilon naught r. Now solving it further, we will get energy will be equal to minus z e square. 4 to the will be 8. So 8 times pi epsilon naught into r. So So this is about energy. Okay. Now next we can, we know the value of R also. So we can put that value of R here, and what we'll get is energy is equal to minus Z times E square upon 8 pi epsilon naught into epsilon naught n square h square upon pi m e square z. This z will go up here, this e square will go up here, so we'll get minus z times square into e raised to 4. Then this thing will also go up, m times pi, and in the denominator we'll have 8 pi epsilon naught into epsilon naught will be epsilon naught square n square h square. This pi and this pi will get cancelled. So we'll be remaining with energy is equal to minus z square e raised to 4 times m upon 8 pi upon 8 epsilon naught square n square h square. Okay, so this is the formula that we have obtained for energy. Now if an electron jumps from an orbit, okay, now when an electron will jump from an orbit I, okay, let us take the initial orbit as I. Initial orbit will be equal to I, and the final orbit is F. We can calculate the change in energy. Change in energy is delta E. Delta E is equal to from initial orbit, energy of initial orbit minus energy of final orbit. Okay. Now this expression will use energy of initial orbit will be equal to minus z square e raised to 4 times m upon 8 epsilon naught square n I square h square. Okay. Minus second one is EF minus z square e raised to 4 times m upon 8 epsilon naught square n f square and then h square. Okay, so minus minus will get plus, so it will be minus z square e raised to 4 times m upon 8 epsilon naught square n I square into h square plus z square e raised to 4 times m upon 8 epsilon naught square n f square into h square. Okay. Now moving further, can take out some common things here. The common will be z square e raised to 4 times m upon 8 epsilon naught square h square into 1 upon n f square minus 1 upon n I square. Okay. And then we also know that energy is equal to hc by lambda. Okay. Energy is related to wavelength. Energy is equal to hc by lambda. So here we can substitute hc by lambda will be equal to z square e raised to 4 times m upon 8 epsilon naught square h square into 1 upon nf square minus 1 upon ni square. Now moving these things here, we have 1 upon lambda is equal to z square e raised to 4 times m upon 8 epsilon naught square. This h will come here, so it will become h cube into c, the whole times 1 upon nf square minus 1 upon ni square. Okay. Now we know that 1 upon lambda is the wave number. Okay. Or 1 upon lambda is equal to nu bar. So write it like this. Nu bar is known as wave number. Okay. Wave number. So we can substitute this nu bar here. So at last we get nu bar is equal to z square e raised to 4 times m upon 8 epsilon naught square h cube to c, the whole times 1 upon nf square minus 1 upon ni square. Okay. Then we can now this thing z square e raised to 4 times m upon 8 epsilon naught square h cube c is known as the Rydberg constant. Okay. So we can write this as nu bar is equal to R into 1 upon Nf square minus 1 upon Ni square. Now, where R is equal to Z square e raised to 4 times M upon 8 epsilon naught square H cube C. This R is known as Rydberg's constant. Okay. So this is the thing that we have got. Okay. And know the energy difference, you just have to calculate the Rydberg's constant. Okay, sorry, you have the value of Rydberg's constant for hydrogen atom, and then you will, uh, put the energy of the orbit F minus the energy of the orbit I. That means the energy of final orbit minus the energy of initial orbit. Okay, and we will solve this, and then you'll get the answer. So, thank you. That's it for today's lecture.